Right now, at opposite ends of the planet, two ice systems that scientists thought they understood are behaving in ways nobody predicted, and they're failing for almost completely different reasons at the same time. In the Arctic, winter sea ice just tied one of the lowest levels ever recorded since satellites started watching in 1979. In Antarctica, a continent that spent decades looking almost immune to the warming happening everywhere else on Earth, has flipped into a decline researchers are openly calling a genuine surprise. Two poles, two completely different physical systems, and both of them just did something that made the scientists who've spent entire careers studying them stop and double-check their instruments. For most of the early 2020s, something in the Arctic data looked almost reassuring. Winter sea ice, the thick cap that spreads across the top of the planet roughly between October and March, had been declining for decades as the planet warmed. But sometime around 2005, that decline appeared to hit a plateau. Year after year, the winter maximum stayed low compared to the 1980s, but it wasn't falling further. Some researchers even described it as a kind of holding pattern, a pause in a trend that had been running since satellite records began. That interpretation held for nearly 20 years. Then 2025 happened, and it fell apart overnight. Between the winter of 2024 and the winter of 2025, Arctic sea ice at its peak growth phase dropped by close to 6% in a single year, the largest year-over-year winter decline ever recorded in the satellite era, a record stretching back to 1978. 6% might not sound dramatic in isolation, but the Arctic's winter ice cover normally spans somewhere around 14 million square kilometers. 6% of that is an area roughly twice the size of Texas, gone in 12 months at the exact point in the calendar when the ice is supposed to be at its thickest and strongest. Researchers at the University of Southampton, working with the UK's National Oceanography Centre, went back and ran simulations to check whether a drop that steep was even physically plausible given current Arctic warming trends. They found comparable events in the model output. Rare, but real. And the simulations captured something else the researchers hadn't expected going in. The following winter, 2026, ice cover ticked up slightly from the previous year's record low. A small partial recovery. The models reproduced that uptick almost exactly, too. Well, that might sound like good news. Ice bouncing back a little after a historic crash. But the scientists were clear about what it actually meant. In every comparable case the model produced, a drop that's steep rarely reverses. The system doesn't snap back to where it was. Instead, it tends to settle into a lower band and fluctuate around that new diminished baseline for years. The small recovery in 2026 wasn't the start of a return to normal. It was Arctic sea ice finding a new, lower normal to wobble around. That distinction matters because it directly contradicts the story that had built up around the so-called pause, a story that, sometimes in good faith and sometimes not, had been used to argue Arctic ice loss was leveling off. The new research makes the opposite case, with hard numbers behind it. The pause was never a genuine stabilization. It was a temporary lull sitting on top of a much longer decline, and the moment conditions aligned the way they did in 2025, the decline picked up exactly where the older trend line had left off, just compressed into a single violent year instead of spread out gradually. NASA and the National Snow and Ice Data Center at the University of Colorado Boulder confirmed the pattern independently. Arctic sea ice reached its 2026 annual maximum on March 15th, at just over 14.29 million square kilometers, statistically tied with 2025's maximum of 14.31 million. For 2 consecutive years, the Arctic has posted the lowest winter peak ever measured since satellite monitoring began in 1979. Jennifer Francis, a senior scientist at the Woodwell Climate Research Center, has compared the pattern to a warning sign on a medical checkup, the kind of symptom that alone might not mean catastrophe, but that keeps showing up on every test, pointing in the same direction. When every number is trending the wrong way at once, doctors don't wait for the crisis to start treatment. Most people picture the Arctic crisis as a summer story, shrinking September ice, stranded polar bears. But winter ice does something summer ice can't. It's the barrier separating a relatively warm ocean, sitting just below freezing, from air above it that can be 60 or 70 degrees colder during the darkest months of the year. When that barrier's thick and solid, heat and moisture stay locked in the ocean where they belong. When it thins or develops gaps, heat escapes into the atmosphere all winter long. And that extra energy doesn't stay parked over the North Pole. It shifts pressure patterns, feeds into the jet stream, and has been increasingly linked by atmospheric scientists to the kind of extreme cold snaps and disrupted storm tracks that show up thousands of miles south in places like the American Midwest or Northern Europe in the middle of winter. The mechanism underneath all of this comes down to something called albedo. Ice and snow are bright. They reflect the vast majority of sunlight straight back into space. Open ocean water is dark, and dark surfaces absorb sunlight instead of reflecting it. So when a patch of sea ice disappears and is replaced by open water, That patch of ocean stops bouncing sunlight away and starts soaking it up, warming the water beneath it. That warmer water makes it harder for ice to reform the following winter, which exposes more dark ocean the year after, which absorbs even more heat. It's a feedback loop, the planet's own thermostat effectively running in reverse, and it's one of the central reasons the Arctic is warming close to 4 times faster than the global average. Now fly to the completely opposite end of the Earth. While all of this was unfolding in the Arctic, Antarctica was living out the exact opposite story for most of the last several decades, which is exactly what makes what's happening there now feel so alarming to the people who study it professionally. Antarctica is a continent surrounded by ocean, not an ocean surrounded by land like the Arctic, and that geography matters enormously. For decades, Antarctic sea ice didn't follow the same warming script playing out everywhere else. While Arctic ice steadily shrank, Antarctic sea ice held roughly steady, some years even expanding slightly, through a combination of stronger circumpolar winds, cold meltwater forming a protective layer of fresher surface water, and the simple physical difference between sea ice around a continent versus sea ice floating in a semi-enclosed ocean basin. For a long stretch, Antarctica genuinely looked insulated from the rapid ice loss happening in the north. Then, in 2016, that insulation broke. Antarctic sea ice extent, gently trending upward or flat for nearly 4 decades, reversed almost overnight and began falling sharply and repeatedly. It hit a record low in 2022. It broke that record again in 2023, with the missing ice alone covering an area larger than the entire landmass of Greenland. Researchers were left asking an uncomfortable question. What changed in 2016 that flipped one of the most stable ice systems on the planet into one of the most volatile? A team working out of the University of Southampton published findings this year describing what they're calling a triple whammy. 3 separate mechanisms compounding on top of each other to drive Antarctic sea ice into what the researchers describe as a self-reinforcing downward spiral. The first is a warming ocean surface layer that has eroded the cold, freshwater buffer that used to protect the ice from below. The second is a shift in the wind and pressure patterns circling the Southern Ocean, tied to something called the Southern Annular Mode, which has been running in a persistently positive phase. Lower pressure over the Southern Ocean near Antarctica. Higher pressure pushed further north. That configuration strengthens the westerly winds circling the continent and has been closely associated with unusually warm, wet conditions around the Antarctic Peninsula, one of the fastest warming regions on the planet. The third is a shift deep in the ocean itself. Changes in circulation pulling warmer water up from below into direct contact with the ice, melting it from a direction that used to stay relatively stable. Individually, each of these forces might have been survivable. Compounding on each other year after year, they've pushed the whole system into a state researchers describe as actively reinforcing its own decline rather than naturally correcting itself. As of the most recent monitoring, Antarctic sea ice extent sits at the 6th lowest level ever recorded for this point in the season, with a sharply divided regional picture, rapid retreat along the Atlantic sector and near the Antarctic Peninsula. While areas closer to the Ross Sea have stayed closer to their historical averages, cooled by unusually strong southerly winds, off an intensified low-pressure system called the Amundsen Sea Low, the same system simultaneously pushing warm northerly air into the Bellingshausen Sea on its eastern flank. It's the same atmospheric feature producing colder than normal conditions in one region and warmer than normal conditions right next door. This regional patchwork connects directly to one of the strangest individual events to come out of Antarctica in years. During the winter of 2024, a season when parts of the continent sit in near total darkness and temperatures typically stay below negative 30 degrees Celsius, East Antarctica experienced a heat wave that broke the models researchers had built to describe extreme events there. Temperatures spiked as much as 28 degrees Celsius above the seasonal average and stayed elevated for more than 2 weeks straight. To put that number in a context anyone could picture, an anomaly of that scale happening in the United Kingdom in the middle of January would push temperatures there into the mid-30s Celsius, essentially transplanting a summer heat wave into the dead of a British winter. That's the scale of what happened in East Antarctica. During a season when the sun barely rises at all, researchers who studied the event, publishing their findings this year in a peer-reviewed climate journal, concluded it wasn't an isolated fluke. It was driven by a combination of a weakened polar vortex, the ring of cold air that normally seals off the Antarctic interior, an atmospheric river carrying an unusual surge of warm, moist air deep into the continent, and record-low sea ice offshore removing a natural barrier that would normally have blocked that warm air from penetrating so far inland. Climate modeling from the same team indicated human-caused warming significantly amplified both the intensity and duration of the event, making an anomaly of that scale far more likely than it would have been in a pre-industrial climate. And the researchers were explicit that this wasn't a one-off. It was a preview of the kind of extreme event likely to become more frequent as the underlying warming trend continues. If a sudden winter heat wave sounds abstract, one glacier's story makes the consequences concrete. Hectoria Glacier, along the Antarctic Peninsula, recently became the fastest retreating glacier ever documented in the modern satellite record. Over a period measured in months, its grounding line, the point where ice transitions from resting on solid rock to floating on the ocean, retreated roughly 8 kilometers, with nearly half of that collapse compressed into an extraordinarily short window. The cause traces back to the shape of the ground beneath the ice. Unlike glaciers sitting on bedrock that slopes upward toward the coast, which naturally slows a retreat the further it goes, Hectoria sits on an unusually flat stretch of seabed lying below sea level. Once it lost contact with that flat bed, there was almost nothing to physically arrest the collapse, and huge slabs of grounded ice broke away in rapid succession rather than the slow, gradual retreat scientists are used to modeling. Researchers have flagged this as significant not just because of how fast Hectoria itself collapsed, but because the same mechanism could apply to other glaciers sitting on similarly flat, below sea level bedrock across West Antarctica, several of which hold enough ice to meaningfully raise global sea levels if they behave the same way. The Arctic and Antarctic aren't communicating with each other. There's no direct mechanism linking a collapse at the North Pole to a collapse at the South Pole in real time. They're separated by an entire planet, different ocean basins, different atmospheric circulation, and completely different geography. What connects them isn't a direct physical link. It's the same underlying driver, a planet steadily accumulating heat from rising greenhouse gas concentrations, expressing itself through whichever regional mechanism happens to be most vulnerable in each location. In the Arctic, that's the albedo feedback loop acting on floating sea ice. In Antarctica, it's a more complex mix of shifting winds, an eroding cold water buffer, and deep ocean circulation changes acting on a continent that had, until recently, been unusually resistant to the warming showing up everywhere else. Antarctica's pre-2016 stability genuinely did puzzle climate scientists, and for years that puzzle got used, sometimes fairly, sometimes not, to argue the whole warming picture was less certain than advertised. But the explanation for that early stability was never that warming wasn't happening. It was that Antarctica's specific geography and ocean circulation were, for a period, actively working against the warming signal showing up in sea ice, buffering it through cold meltwater layers and strong circumpolar winds. Once those buffering mechanisms started breaking down around 2016, exactly as the triple whammy research describes, Antarctica stopped being the exception and started catching up to a trend that had already been running in the Arctic and almost everywhere else for decades. The pause was real. It just wasn't permanent. Sea ice loss at the poles doesn't directly raise sea levels in a major way on its own, because floating ice, like an ice cube already in a glass of water, has already displaced its own volume before it melts. The sea level danger comes from land-based ice, glaciers and ice sheets sitting on solid rock, like Hectoria. Every meaningful acceleration in the collapse of those glaciers translates directly into rising coastlines everywhere on Earth, not just near Antarctica. But sea ice loss still matters enormously, because it's one of the primary triggers accelerating everything else. Less sea ice means more open, dark ocean-absorbing heat. More heat in the ocean and atmosphere destabilizes the land-based glaciers nearby, the ones that do directly raise sea levels. Less Arctic winter ice reshapes pressure systems that influence storm tracks and cold outbreaks across the entire northern hemisphere. And a weakened polar vortex over Antarctica, the same mechanism blamed for the 2024 winter heat wave, has documented links to disrupted weather patterns, reaching into the mid-latitudes of the southern hemisphere. Researchers tracking both poles have started using a specific term for a scenario they're watching for at both simultaneously, a blue ocean event, referring to the moment sea ice extent in a region falls below roughly 1 million square kilometers, low enough that satellite images would show overwhelmingly open, ice-free blue water rather than the white expanse people associate with the poles. It doesn't mean all polar ice vanishes. It's a seasonal regional threshold, not a permanent planet-wide loss. But researchers have raised the possibility that an Arctic blue ocean event and an Antarctic blue ocean event could theoretically occur within a similar window in the coming years, something that has never happened simultaneously in the satellite era. The Arctic and Antarctic figures referenced throughout come from microwave radiometer instruments carried on multiple satellites, including sensors operated jointly by Japan's National Institute of Polar Research and the Japan Aerospace Exploration Agency, alongside NASA and the National Snow and Ice Data Center in the United States. These instruments don't rely on visible light, meaning they can measure ice extent continuously through the total darkness of polar winter and straight through heavy cloud cover, conditions that would make ordinary photography useless for months at a time. That continuous all-weather coverage is why the record stretching back to 1979 is considered so reliable, and why a 6% single-year Arctic drop or a sixth lowest Antarctic ranking aren't treated as noisy estimates. They're precise figures that multiple independent institutions in multiple countries arrived at separately and then cross-confirmed against each other. It's also worth remembering that this satellite record, as long as it feels, only stretches back 47 years, a blink of an eye in geological terms. Every record broken in 2022, 2023, 2025, and 2026 isn't just a record within living memory. It's the lowest point ever documented by direct instrumentation, full stop, with no equivalent baseline from before the satellite era to compare it against. Exactly why researchers keep reaching for the word unprecedented rather than simply unusual. Two enormous complex physical systems, each with decades of relative stability behind it, have both entered periods of measurable, well-documented, mechanistically understood decline at the same time, for reasons specific to each region, but tied back to the same root cause. That's not a prediction dressed up as certainty. It's what nearly 50 years of consistent satellite measurement, cross-checked by independent research teams across multiple countries, is currently showing in the data itself. If stories like this, grounded in the actual research rather than the scariest possible headline, are why you're here, subscribe so you catch the next update as this keeps developing. And tell us in the comments, which surprised you more, the Arctic's sudden crash after 2 decades of apparent calm, or Antarctica flipping after decades of looking like the one part of the planet holding steady?